Welcome to Resilience Unravelled, your regular guide sharing tools and expertise to build a life full of positivity and possibility. Here's your host, Russell Thackeray.
So today I'm very excited to be talking to Dr Mark Changizi, and Mark and I have been trying to arrange a podcast session for a number of months, haven't we, Mark?
That's right.
And so where are you talking to us from today?
Ohio, Columbus, Ohio.
Oh, that's fantastic. It sounds very exotic.
Sure, let's imagine that.
Yeah, okay. So, Mark, you've got a very. How would you describe yourself? How would you describe what you do?
Well, I'm a bit of a theoretical cognitive scientist. So I'm a psychologist, cognitive scientist, neurobiologist, but I'm more of a theorist. My PhD is mathematics, and so I devise rigorous theories and then go setting about testing them empirically in some manner. And my focus is usually on evolution and evolutionary principles underlying why we are the way we are. Rather than the billiard balls that are bouncing in your brain, I'm more interested in why your brain is doing those kinds of things rather than some other kind of thing. Why we evolved to do the kinds of computations or have the kinds of eyes or body structures that we have.
Wow. So how did you get into that discipline?
Oh, well, I mean, if I look back at my high school essay, in the United States we write essays for college when you're still in high school, and my aim when I go back and read that was to answer the questions to the universe, which is something I was saying ever since I was little. But I wanted to eventually go study, at that time I was saying things like study consciousness and how a bunch of atoms can become conscious. I've never in fact worked on consciousness. It turns out it's a big morass trying to do that. But I was interested in the kinds of questions like neuroscience, understanding thinking. But I even wrote back in those old essays that for undergraduate and even for PhD, I didn't want to do those things. I needed to learn math and physics and computer science in order to have the foundations that I needed to study those kinds of questions.
Right.
So I first went into math and physics undergraduate and then a PhD in mathematics with the idea that those are the kinds of tools that you have to be a good theorist in cognitive science and neuroscience. Right.
And so how does your professional development work? I mean, are you attached to a university? I mean, it sounds interesting, a different sort of direction to what I normally hear about. So I'm intrigued to know how you become a theorist.
So after that, I postdoced at various neuroscience labs and was able to get to. I was at Duke and then I was at Caltech as a sort of a theoretical neuroscience fellow, and then I became a professor at RPI, Rensselaer University, which is up in upstate New York, as a CognoScience Professor. And then eventually I started my own lab. The idea I didn't want to beg for money from the government for grants anymore. And I decided with a colleague to start a research institute of my own and our own, funded by startup tech companies that come out of my research. So I have a medical device company that, roughly speaking, comes out of my research in color vision. The idea is paramedics or nurses wear these protective eyewear. They're just regular protective, no batteries or anything, but it enhances your ability to see veins. So I have intellectual property patents that come out of my research and sort of patents related to it that led to this company, and that's sort of the useful stuff that I do that now funds the basic research that I continue to do.
So that must create quite an interesting and dynamic culture over there, the way the funding works. So you've got no central source of funding. You have to link it to some sort of commercial enterprise, do you?
For me, that was much preferred to buy my intellectual freedom, because in university, you are stuck for the rest of your life begging for scouring the grant announcements, and then trying to convince yourself that what you do is what they're asking for, which it never is. And then you make up some story about how you're the right person for that. And it's not even what you'd even like to do. What you really were romantic about, you gave up long, long ago because you got into this grant game of keeping your existence in university by just finagling ways to get grant money into your lab. And so it's really a soul-killing, intellectually crushing environment that you're asked to fare. these days in academics, and I got sick of that kind of style, and so I wanted to buy my own intellectual freedom in the way that I did, which was my own route.
So it must have been quite a risky sort of decision to sort of branch out in that direction, was it?
Yeah, I wouldn't have done it 10 years earlier because so at least I had enough discoveries under my belt and enough books under my belt, so I felt comfortable to, when you're younger, you want to have a shingle, you want to have your address look sexy. You'd like to have a fancy name. You would like to have Dr. Mark Changizi, professor at such and such place, some fancy name. That's what you kind of want. And then later, maybe you have the guts to have just put your own shingle up. It just has your own name, and it's just the name of our lab is 2AI Labs. But there's no inherent gravitas from it, other than anything that I and my colleague bring to it. So that's always a scary thing. But you're certainly not comfortable to do that when you're too early in your career.
Yes. So I mean, you must have one of those continuing dilemmas about running an IP operation and how you protect your IP and how you sort of monetize IP. But so it seems interesting that you've gone into this way of VCs and medical devices. So is that an established route over there?
Established for, I mean, there are in certain engineering fields. There's a culture where some significant fraction of the engineers at top universities will have some sort of startup company in conjunction with their professorial trajectory. In my own field of neuroscience, it's not part of the culture at all, or CognoScience or psychology, to do that. And I didn't try to do it in conjunction with maintaining my professor position. So as far as it's a rare thing. I know of some other colleagues that did this, and they were in cognitive science departments, but ultimately they were actually engineers to begin with. They were more AI sorts. So it's not your typical route. And a lot of people think that I was crazy. There's this idea that finally you get your tenure track job, you finally get tenure, you're at this dream job. Why would you ever leave it? But in reality, there's a lot more constraints and things to think about. And buying your intellectual freedom and having the ability to work on what you actually think is the most important job for you to work on, research-wise, it's very hard to continue that at even later stages of your career because of the kinds of cultural pressures that are inherent to being in a department and being at a university.
So how do you manage the sort of cultural compromises you need to make between the academic world and the sort of highly, the sort of world of the VC? Because I mean, they're very different, aren't they?
Well, in VC, we're actually we never took VC. We're trying to organically grow. So I haven't had to. If we ever took VC, they would put their hooks in me, all of the investors, and make me run around like a rabbit all over the country. Yeah. And probably I'd lose the ability to do the research. So my goal is to organically grow the company so that it funds the research, but it doesn't require so much of my time that my research career is over. So that's the fine line that I'm trying to walk.
So actually, it's actually quite inspirational to hear about someone who's a researcher really standing up on their own and creating a commercial enterprise around them. It sort of gives people hope in universities that they don't have to sort of take the traditional route. They don't have to, follow conventional wisdom. There is an opportunity later on to diversify and sort of step out and branch out on your own. Yeah,
and there are risks of its own, of course, because it's a difficult. The standard story of how someone becomes successful as a business owner is that you work for 10 or 15 years and you have very little life. You work 80 hours, 100 hours a week, and then it happens maybe that someone buys your company or however it works. But that's not the kind of success story that I want, because I'm actually doing this to maintain the research that I want to do and to buy myself more intellectual freedom, to be able to work for 4 years on a single massive project, let's say, rather than having to publish 2, 3, 4 papers per year and constantly get grants forcing me to do things I never wanted to do in the first place. So, this kind of business strategy is trying to make a business work and yet still maintain all that kind of research time, which is a different kind of growth for a company than you typically have as a CEO.
Yeah, interesting. So tell me more about the research you've done and sort of the insights you're pulling at.
Well, I tend to. I've always tried to not look back on a field once I've left. My attitude as a theorist is that the odds of me having another good idea in that field are practically zero once I've already had a good idea.
Right.
And it can be really easy to try to maintain. Once you have a good idea, it's very easy to say, I want to do the next step. It's easier to get grants. And you want to make sure that good idea really becomes secure in that literature, so that you can, when you die, you can think to yourself, oh, I made that idea stick. But if you do that, the problem is that there's all these other ideas you'll never find yourself wading into if you just try to keep digging in that previous holes where you found some gold, and there might be much bigger and much more interesting gold out there. The reason I'm saying that is that I have research discoveries and contributions in areas of perception, like why we see illusions, or why we have color vision, or why our eyes face forward. I have things that are more morphological, why your fingers get pruny when wet, or why you have as many fingers or limbs as animals do, or why your brain is shaped the way it is, or scales, why large brains are convoluted compared to small brains being smooth, and the different kinds of changes that brains undergo when they go from small to large. I have research on culture, like how is it that we came to write and have language and have music. So there's a variety of different kinds of things and my current research is on the origins of emotion, and hopefully a book will come out of that in 2 or 3 more years. So what would you like to hear about?
Well, actually, I could be really trite here and say all of it, because it's all fascinating. But talk to me more about the colour vision. That's quite interesting, because I believe cats have black and white vision, and we have colour, don't we?
Right.
So what's that about then?
So most mammals have 2 dimensions. They have black-white, but they also have blue-yellow. The average mammal then has sort of a 2-dimensional palette. Blue-yellow being opposites, sort of a one axis, and then a black-white grayscale axis. Then it's only some of us primates that have red-green vision, this 3rd dimension. Now, for 100 years, they had thought that maybe we primates have this 3rd dimension, so that we can find fruit in the forest or young leaves. It was eating related. And I argued that that wasn't a very good argument on its face, because the kinds of variety of fruits and edible things for which you can distinguish, we all have the same exact kind of color vision, the red-green primates, the primates that have red-green vision, yet the kinds of diets are incredibly diverse across the primates and even within primates.
Right.
And so the argument for it being the optimal kind of color vision for that is a very weak one. But it had occurred to me, that another thought was that color vision is actually for seeing health and emotions on bare skin, and it turns out that in order to see blushes and blanches and all of the color states that are on bare skin, as well as when you're able to see veins, for example, and all of the things that you see, and the glow of youth, when we say that the beauty of skin, it's because you're really seeing through the transparent skin to the blood below. And in order to see one of the main signals that is going on with blood, which is how oxygenated your blood is, which is mentioned if you're ready to collapse because you've been running too hard or something like this, you're very deoxygenated. You're not getting good oxygen to your blood, and it's not being distributed around your body. Right. Then this is something that's visible to you. But in fact, it's only visible to you because you have eyes that are peculiarly optimized, a kind of color vision that's peculiarly designed to see oxygenation variations of the hemoglobin under the skin. And you can, in fact, show this. You can show that we have a really peculiar kind of color vision. Instead of having, like your cameras have 3 filters that for RGB, red, green, and blue. The blue filter's down low, and the green filter's sort of in the middle, and the red filter's up in the higher in the 600 wavelengths areas. And so it uniformly samples the spectrum in 3 different spots, and that's what you'd kind of expect. Birds and other vertebrates that are non-mammals that have actually 4 dimensions of color vision, they typically have their cones or their receptivities at 4 different parts of the spectrum, but they're uniformly distributed across the spectrum. What's peculiar about we primates, our red-green vision, is that whereas we had 2 cones before, 2 kinds of filters for absorbing light at different parts of the spectrum, the new filter, the new one that lets us see a 3rd one, is exactly next to one of the earlier ones. So we have one low one in the 400s, and then we have another one that's almost in the exact same receptivity it's sensitive to the same parts of the spectrum as the other one. They're not uniformly distributed at all. It's a terrible engineering design, except that it's not a terrible engineering design if what you're trying to see turns out to be the blood under the skin and the oxygenation modulation, so the hemoglobin. Because in order to see this very peculiar protein changing its structure as you get more oxygenated and deoxygenated, it turns out you have to have exactly that peculiar kind of color vision. And so that's one of the things that I showed in that paper. And it also turns out that the primates with color vision are also the naked primates. The ones with bare skin are the ones with color vision, this red-green color vision. The ones that are without red-green color vision are furry faced, like your typical dog and your typical bunny rabbit and typical mammal. So nakedness and color vision, red-green color vision, go together. It's really all about seeing skin and the states that you can see through the skin.
Oh, so is that why, as humans, we can sort of pick up on people's emotions? I suppose we call it intuitively, but what we're actually doing is just effectively looking at the amount of oxygenated blood pumping around.
That's right, and you see gradients of it. That's different kinds of emotions. Be very subtle, but there'll be a slight spots on one part of the cheek that does change, and other parts that are changing less. And it's these changes in the distributions of blood, not just on the face, but even, of course, the genitalia. The genitalia are also signaling very strongly, and in other primates, very, very significantly. The rumps change depending on the state or the estrous state, and depending on how angry a male is. That all of these things signal different kinds of states. And, of course, we pick up cues to emotion in other ways besides color. We just see the facial expressions and the bodily expressions as well. But that's one of the key ways, and it's mostly implicit, our understanding. We're not usually consciously aware that we're reading these signals, but we've been designed to see them and to understand them and to react to them appropriately.
So when you're... it sounds quite open to... the usual levels of human misinterpretation. So if I look at someone who blushes a lot, you often see people that blush from effectively the roots of their hair down to the toenails, don't you? You see people like that. Is that something that's going wrong with that system then? The way that blood's flowing, or is it just that I'm misreading it?
Well, I mean, there are obviously are different. There are folks that are much more prone to blushing, for example, than other folks. And there are folks for which you can, one, they could be having just a lower threshold that makes them show signals that we otherwise wouldn't. Sometimes they may just have the kinds of capillary systems that's in their cheeks may be just more perfused than in somebody else, and so you can see it more easily. And so all of these things can modulate the degree to which you see the emotions in somebody else. And you can imagine maybe there's even advantages. I don't have any specific ideas. Some people showing more emotions could sometimes have certain benefits, and sometimes maybe there are certain downsides to it as well. And there's a lot that you find maybe some degree of variability across people.
So in a way, we all meet people who are very buttoned up and repressed and held together, but actually they give themselves away, I'm thinking, through this sort of emotional cue in the way that their actual skin flushes and changes colour.
That's right. So that's one difference between emotions on the face, the muscular emotions on the face, is that whereas you can, to some degree, physically, consciously control the muscle, the emotions you're trying to show on the face, you can't control your cardiovascular system. You can't control the degree to which capillaries show themselves near the surface. All of these things are out of your control, which is also why color-based emotions on the skin are more honest, we say. So that if you really are showing blushing, that shows that you're really sorry. If you're blushing by virtue of an apology or you're really embarrassed you've done something wrong, it shows that you're truly sorry in the sense that you couldn't fake it, whereas just merely saying sorry or showing sorry with some other muscular facial reaction could be fake. But it's much harder to fake. It proves to the person you're trying to say sorry that your cardiovascular system, which is out of your control, really feels sorry.
Wow. And so how does this link into your work understanding where emotions come from? Is there a link between these two things?
There's actually not much of a link. And the research on color vision, and that connects up, of course, to the medical device company, that goes back 10 years ago. This new stuff is actually, which I'm probably not going to talk about too much. One, because until the book is written, sometimes
No,
the way to tell the story is actually is in flux. And I'm not sure exactly the best way to explain it. I'll be more flat-footed in how I'm explaining things. But two, it's actually quite different. It's really trying to derive and understand from first principles why social creatures will have not just the kinds of emotions they have, but how they're structured, how they're organized into one piece of machinery, and with sufficient clarity that we can actually build artificial intelligence that actually runs these things, has these emotions, knows how to respond, so we actually can just really understand the computations and why we have them the way they are, and the entire structure. There's a grand unifying theory of emotional intelligence, social intelligence, and emotions and things like this. So I'd say it's utterly a distinct kind of thing from the color.
Now, I'm very much looking forward to seeing that, because I've done tons of research in sort of application of emotional intelligence and social intelligence in my own world. So I was just intrigued to know if there was a link. So the medical devices you come up with have been linked to the colour research. So
that's right.
So how does that work?
Once we realize that once you figure out the connection between how the cones, this peculiar kind of color vision that we have, is designed for seeing the oxygenation signal on hemoglobin, then you can start asking whether or not we can enhance it. So it turns out that when you get more oxygenated, the skin looks redder. Less oxygenated, it looks greener. But it turns out there's some very narrow parts of the spectrum where, because of the peculiarity of the hemoglobin protein structure, something funny happens in that area. So if you look at just some little narrow bands, those narrow bands are contributing to the opposite. When you get more oxygenated, those narrow bands are actually contributing into being greener rather than redder. So we basically realized that if we can come up with build filters that block those narrow bands, then you're actually going to, when someone gets more oxygenated or less oxygenated, the red-green differences are going to be even stronger because you're getting rid of the bad signal, basically.
Ah, really?
So by just blocking, and because the bands are narrow, you're blocking not much at all. You're barely blocking anything. And so the world looks effectively the same. This is one of our technologies called the Oxy-Amp. Paramedics wear these, nurses wear. And so you're basically blocking nothing. Everything in the world looks the same, except that veins and anything that's color modulations on the skin that are health-related are exaggerated. The oxygenation dimension is exaggerated. And so even for color normals, emotions are enhanced. So we have poker players, although we don't market it for this, poker players that had seen stories about it and asked us for mirrored versions, because they want to wear mirrored versions so that their eyes are covered, and they'd like to get the enhancement on reading their opponent's faces. So we've have a number of them that would have bought it just for their reading the tells of their poker opponents.
Oh, interesting. I assume you didn't think of that when you first sat down to create a medical device.
Yes, certainly. The idea of reading people's emotions and reading lies and people to wear them on dates, all crazy kinds of ideas came up to us. But maybe we had mentioned poker, but we certainly didn't think that would become something that people would buy.
Now, one of the reasons we actually found you in the first place is because you'd written some interesting. I'm just switching direction now. I'm coming to the idea of culture, language, and music, which you alluded to earlier. And I know you've done some research around music and birdsong.
Yeah. Now, I've done some research on birdsong long ago that was unrelated to the music research.
All right.
And it was a. People often look at birdsong as an example of song, and I don't think it has anything to do with song, even a little, or even language and a little. And actually, one argument for that is that if you look at language-like things, then when you look at, so for example, if you look at how a small child uses language compared to a larger child who uses language, if a small child only has 10 words, then let's suppose he talks 100 sentences with his 10 words that he or she can do. But once the kid has 20 words, he does more than 200. He doesn't just double the number of sentences. He doesn't just have 200 sentences going from 100. He has disproportionately more because he uses those 20 in a combinatorial explosion way. And so that you can see by when you have more words in your language, you can have a combinatorial explosion. You don't just, when you double the number of words, you don't just double the number of sentences, you much more than double. because you use them combinatorially. But what you find in birds is that when you look across birds, and the data, this is from 10, 12 years ago, the data set that I was able to pull together, when you look at birds, if you have birds that have 10 times the number of words, or these are called syllables, sort of bird basic kind of, the ones that have more syllable types in the repertoire, and then they have the number of different songs that they can build out of those. The birds that have more words ended up with proportionately more sentences. So whenever you double the number of words, you double the number of sentences, which meant that they weren't, in fact, using their words combinatorially. It was just, it's like just having canned sentences, just sentences which are always just like certain sentences we have in English are not really combinatorial, like they're just phrases that we say that happen to have multiple words in it, but we treat it like a single entity. So nothing's coming to mind right when I say that at the moment.
It's like, it's like some of those default phrases on your iPhone.
Yeah, default phrases that have that are just used as we just say all the time. So that's what birds are like. So that was that's one of many kinds of arguments that bird song is a misnomer, and I don't think anyone was trying to make a big, strong theoretical claim when they started calling them bird song. But somehow by naming them that, they ended up often being thought of in light of, or as an analogy with our kinds of music or our kinds of language, and I don't think there's anything similar about that at all.
But you're saying there's something significant about the fact that we have music at all.
Yeah, so music is an entirely, and language is different kinds of things altogether. But before I mention music, it might make more sense, a similar kind of story for how we came to have music is also for how we came to have writing and reading.
Right.
And the reason I think it's somewhat simpler to start there. And we read incredibly well. Most of us read more than we listen to words this day and age. It's in every room of the house. We read by the time we're 4 or 5 years old with relatively little training, which although it's much later than we speak, it's still, considering that we're being spoken to ever since birth, we're not being shown words, it's incredibly early. Most of us can read before we know how to somersault, and then we can do basic primate kinds of things. So reading is we're incredibly good at it. We're so good at it that it seems to be the kind of thing that's an instinct. If aliens were to look down at us, they'd imagine, it has all the hallmarks of instinct, and something that we've evolved over evolutionary epochs to have parts of our brain which are designed for reading and writing.
Really?
But of course, aliens might think so until they study this further, because we know, of course, we didn't evolve to read and write. Writing is much too recent. It's only several thousand years old, and for most of our lineages ourselves, we can go back to grandparents or great-grandparents 2 or 3 generations back, and they were all illiterate.
Yeah.
Most of the time that writing has been around, nearly nobody, nevertheless, could read, except for some small number of accountants and bards or something like this. So it has had no evolutionary effect on our brains. Our brains are our same illiterate ancestral brains that we've always had. So how is it that we can read and read so well that it seems like we're having instinct? And the argument is that once culture got up and running and trying to build writing systems for us, then culture was able to design writing systems that are good for our brains. And what kinds of writing systems would be good for our brains? What are our brains good at seeing and processing? Well, they're good at seeing and visually processing natural scenes. And what are in natural scenes? Well, there's all these 3-dimensional objects, the opaque objects just strewn around your environment. And it turns out that 3-dimensional objects strewn around your environment have certain kinds of ways that the contours intersect one another. Like L-junctions is one case where just 2 contours out there intersect at their corners, at their tips.
Right.
And if you look around the room, you'll see a lot of L's. T-junctions are where one contour goes behind another contour. And that happens whenever objects are in front of other objects.
Right.
X-junctions, actually, where 2 contours cross, are actually very rare. Remember, contours are always at the edge of an object, and so to get a real X-junction, you need actually something like partial transparency. So you're looking at things that are partially transparent in front of other partial transparent things, and you can get X-junctions, but it's very rare, in fact. And so I was able to characterize, those are the cases of just 2 junctions, and the kinds of cases of 2 junctions, 2 contours that make a junction. What if you allow yourself 3 contours, like Y-junctions, where you have 3 intersecting at a point, or Z-junctions, or Ks, and you can characterize 32 of these different kinds of junctions. And it turns out that some of these kinds of configurations of contours you can show in a variety of ways they happen in nature, and some of the kinds don't happen in nature. But all of these kinds you can perfectly well write. You can rewrite them with your hands. But what we find is that the ones that happen in nature, and the more commonly they happen in nature, in natural scenes, are the ones that we find more commonly across writing systems. Because these are exactly the ones that happen commonly in nature that you should have visual brain regions that are good at processing.
Yeah.
If they don't happen in nature, your brain's going to be bad at processing it because it had never any good reason to process it.
Yeah.
So the argument is that the writing systems are shaped to look like nature because that's what we're good at processing. And that's how culture harnesses a brain that's illiterate and turns it into a literate brain by changing writing to be something that it's good at processing. In fact, now we actually have areas of our brain which neuroscientists call the visual word form areas, is in fact the name of the area.
Wow.
Because they're so specialized at recognizing words that they've decided to call it that. Of course, they're not confused into thinking that it actually evolved over evolutionary epochs to recognize words. It's just, but you can imagine aliens being confused for again the same reason. But it's a case of harnessing. A case of culture bending over and being engineered by a noted designer in particular to shape these things to harness our brains so that it converts those mechanisms into doing a new kind of task that it wasn't originally planned for.
Wow. So that makes a lot of sense. So how does music fit in then?
So music and speech have similar stories. So the case for speech is just a much older case of harnessing. Instead of having to argue that, and the standard story for speech is that it's potentially been with us long enough that we could have evolved over evolutionary epochs to have speech areas in our brain that allow us to speak, and speech processing comprehension areas in our brain that can allow us to comprehend it. But once you see how the story works for writing, and you say, wait a second, in a much shorter period of time, in just several hundreds and hundreds of years, we could have writing systems that figured out how to shape themselves to be well-formed so that they can harness our brains. Well, we've had potentially hundreds of thousands of years for spoken language systems to shape themselves, the sounds that they are, to be well fit to our brains. In this case, rather than it being about seeing three-dimensional objects in the world, it's about recognizing auditory events. All of us mammals and many of these kinds of, all the kinds of animals in terrestrial environments are good at recognizing the kinds of sounds that occur there. And sounds are built out of certain kinds of structures, and you can work out what I do in my book, Harnessed, is work out the kinds of sounds that occur within object events. Like, for example, they're built out of hits. Most objects are solid objects in our world, and they can hit each other. Or one object can slide along another one. And whenever an object hits or slides, the objects vibrate, or they ring. Those are the three basic atoms of sounds in our environment. And in fact, they already align with the three basic atoms that we find in language, which hits just sound like plosives, like p, k, t. Slides sound like fricatives. And rings, which is what happens when any object hits anything, they vibrate, sound like vowels and the other, what we call sonorants, like wa, ya, and any of the kinds of more complicated vowel sounds that themselves change as you say them. But it's not just those three atoms that align between the sort of solid objects and the phonemes or the language world, but then you can start saying, well, in fact, most events don't start with a vowel, they start with a sonorant, they start with a hit or a slide, because that's what causes the rings happen after hits or slides. And which is also why we find in languages that the basic thing of a syllable is ba, or pa, or sha. It's not, the basic sound in language is not ab or yad, and the other way around. It could easily be that way. But those sound like backwards events. They sound like, when you play something backwards, it sounds like yap, yap, yip,
Yeah,
yap.
that's right.
That's backwards sounding things. That's not real life.
Yeah.
And we don't like our syllables that we build words out of to sound like that. Why? Because our brains are not good at that. They could be good for that if they had evolved in a world like that, but they're not. And they're not because of the way the natural auditory environment, natural events occur. So that's just the beginnings of the story for how language, spoken language, harnesses our auditory recognition event system.
So, Mark, I'm having thousands of ideas here. So, is this why? It's two questions. So, is this why older classical music like Haydn and Mozart and Beethoven sounds so easy on the ear? Because actually, it's using these sorts of patterns, whereas polyphonic music, so more modern weird music, sounds peculiar because it's not using those logical sounds in the sort of more traditional way, the more obvious way.
Well, yeah. So I was building slowly up to from writing systems to the auditory case of spoken language, and then into the music, which is different than language. There are some similarities only to the extent that language often has a prosody to it. That when you're speaking, your voice goes up and down, and when you ask a question, you might say, "Are you going to go over there?" And the person says, "Yes, I'm going to go over there." Sort of ending, the rises in how the intonation goes up and down. But other than that, language and music are very different stories. And the story of music, I argue in that same book, Harnessed, is, and it was a struggle for me actually for a while, because I had already worked out the stories and the research for writing and for speech language. And the question was, what else do we use our auditory systems for besides listening to people talking to us? And of course we use it for hearing sounds in the world, but I had not really sat down and become very grasshopper, like in a karate way, like listen grasshopper to the sounds around you.
Yes.
To realize, of course, none of the other animals that have auditory systems have, language, and of course they're using it for the natural environment. And but the main thing that led me to the following idea was that music is incredibly evocative in a way that language is not. Language can sometimes sound interesting, but we're not going to listen to it all day. Most people are happy to listen to music 24/7 if they could. They have it on in their car. They have it on in their ears while they work. They have it while they're working out. They just have it constantly with them, and it's evocative. It can make you cry. It can make you move to it. Typically, the kinds of stimuli, whether they're visual stimuli or auditory, that have that kind of effect on you are usually the sounds of other humans. It's not the sounds of horses that you want to listen to. It's not the sounds the things that are most evocative to any creature are other creatures of the same species. Yeah. They're the ones that usually that you're going to have the greatest evocative response to. So in what way could music in fact be the sounds of people? Well, in fact, the idea is an old idea going back to the Greeks, and it's not really my idea, the basic point here, and it's been thought of many times, that music sounds like movement. And it's long been thought that music sounds like movement. And sometimes it's more of a metaphor, and you're not even sure exactly who's moving and what's moving. But people have also thought, well, could it be sounds of a person moving? So what I do in the book is go step by step and show what kinds of sounds do humans in fact make when you move, working it out in detail. You have, of course, footsteps, which provides a beat. You have time-locked rhythmic things that occur with those footsteps, depending on the kind of gait that you have and the way that your arms are swinging, the kinds of sounds that your body makes when they move. And these are all rhythmic aspects, like the rhythm relative to that basic beat. You have loudness modulations, depending upon mostly about how close you are to the other person. So if you're a listener, as the person gets closer, they're much louder, and as they go far away, they're much less loud. And you also have pitch modulations. That is, they go higher, and it's much more subtle than what I just did, but for a person moving. But these are Doppler pitches. When a train goes directly toward you, it's high pitch. Yes. When it moves away, it's low pitch. Yeah. And these things happen in the natural environment as well. And so the meaning of pitch is very often what it means is the direction of the mover relative to you. Higher pitch meaning more directed toward you, and lower pitch meaning more directed away from you. And you hear this all the time. For example, if you're walking on the street, imagine you're walking and the cars are coming behind you, so you're not even looking at them, and you're walking on the curb. And the cars are passing you. They're 1 meter away from you that they're passing. Yeah. And their sound, the loudness of the car is perfectly consistent with it being about to crash into you. Yes. Because it gets very, very, very loud. But what's the reason you're not even slightly afraid is because the pitch is going like this. Yeah. If ever, and that's because it's passing by you, and you hear that you're not consciously thinking about it, but if ever you were to hear and it just, or now it's veering towards you in that case. It actually is, oh, I like the look of this guy, I'm going to get more points if I run over this guy. That's very different. You would hop out of the way.
Yeah.
But you're so good at reading the pitches that you don't even notice that you were doing that. So pitch is a cue to the direction. And so what I argue and show is you can say, well, here's when people are moving, they typically move this fast or this tempo. And so, and do you find that music tends to have tempos in the same speed as human range? And people, when they turn at these typical rates and this distribution of rates. Does music turn, quote unquote, turn just as quickly? And what that means is when a person turns 90 degrees and if you're around them, that means that they've gone from the highest pitch of coming directly toward you to, let's say, the middle pitch, which would be right in between their lowest pitch. So you can actually talk about what it means for a music to turn, and you can actually ask, is music turning at the same angular rates that people are? And you can do this over and over again. There's like 60 or 70 of these different kinds of regularities that you can show that humans make. And do you find the equivalent regularity, once you understand what that means musically or sound-wise, do you find that when you look across lots of data across music? And over and over again, you find that these peculiar regularities, you find that at the signature of human walking and human movement are found in the structure of music. The idea being that composers, even though they don't consciously think about it like this, they feel in their bones that this feels like an interesting story. It's a story of a person moving around you, approaching you, moving away, dancing toward you again, evocatively, and then getting angry and moving away. All of these things, they're not consciously thinking about it as a person, but it evokes their lower auditory recognition system, but it's their auditory human emotion recognition system. It's their human behavior recognition system. And that's what they're utilizing when they're good composers, and that's why it feels good to them, and that's why it feels good to us, because it really is a story about a human, an evocative mover in your midst. And this is why, and also why we dance to it. Why does choreography want to put people moving to music rather than books falling off shelves or water jiggling or jello jiggling or any number of billions of other things you can do? 99% of the time it's people moving to music when they build a video. And it's so obvious in that case. Well, it's because music is really about a person moving. That's what it is. But it's done at the level that your lower auditory system understands, and you're not necessarily consciously aware of it.
So there's something that taps into the sort of fundamental nature of being human then in music.
That's right. The music for a dog could have some similarities. So, for example, the pitch modulations over time could have some similar, like dogs might approach other dogs and they go away and they come back again. There's going to be some similarities, but they're going to have different beats because they're quadrupeds, not bipeds. They're going to have, and of course, they've got a much more complicated gait. They have different gaits as well. You can imagine this for dogs. You might have starting from, I don't know, it's probably more complicated than the choices that we have between 3/4 time and 4/4 time, because they can suddenly go from a trot to a whatever the other, to a gallop and all the kinds of equivalent things, which would have a very different feel to it. And their gaits are going to be at much faster rates. And so what music would be for dogs, were dogs to get culture up and running well enough that it could design music for dogs over time that was really optimized for the brain, would be highly different than it is for us, for example.
So I'm resisting the urge to ask if dog music's written by Johann Sebastian Bach, so I shan't say that. So when we're thinking about some of the music that's written for people who are stressed, and talk about this idea of linking music and stress together so stress reduction can happen. So that's a thing. That's actually genuinely, evidentially sort of unprovable, I suppose, that those two things can be linked together, music and stress reduction.
There's a startup company and I know the fellows involved in this, and they've been around for a while. And I tried to they came at it from an angle that was quite different from my own, and I was trying to get them more up to speed on the way I think about music, because I thought it could really help them.
Yes.
At having a more theoretically driven way of composing music that would be stress reducing, rather than I think they were more using a typical composer's way, or a more inspired, more inspirational way rather than theoretical. But yeah, you can I mean, we know that you can make you recognize an angry walk. You can recognize a sad walk. You can recognize a happy walk. these are well characterized. The gaits have particular characteristics to the way that the footsteps land, and then you can recognize it, as well as not to mention the way that the sequence of behaviors that they do, not just the individual footsteps, but the sequence of things that they do around you, which are more complicated for scientists to understand, are, I'm sure, well understood by your brain. You can tell when they're huffing and puffing around the house as opposed to whether they're floating around because they're they're just really happy. And these things then can be put into music in the right doses in the right way to make you more stressed, like certain kinds of music like to do. And it's sort of, young kids are banging their heads to it, and in other ways, at the right doses to try to calm you down.
Wow. I'm having more ideas here, and I definitely want to talk to you about something else outside of this podcast, which would be interesting. I'm conscious of your time, Mark. I've just noticed. Sorry, I thought we'd been chatting for 5 minutes. I just realised we've been going for 45. It's just time's just flown. If someone wants to read some of this work of yours, where should they look? Is it Amazon for Harnessed? Is that the best place to get that book?
The two previous books, I've got 3 books at Amazon. The last one was Harnessed, on the origins of music and language, and the one before that was Vision Revolution, which is on color and why your eyes face forward, and where the writing systems and why we see illusions and things like that.
Mark, it's been an absolute pleasure to talk to you, and I've got so many thousands of ideas and things to ask you, which we just don't have time to do today. But you've really brought the sort of subject to life, and you've answered for me one of the fundamental questions: why we are so. I mean, why music is good for us almost. It's like a form of medicine, isn't it? Because actually we are part of music, and it's part of us in a way. And I don't without getting too spiritual about it, but it's a fundamental part of the human condition, isn't it?
It's become. I mean, obviously, it's not fundamental in the one sense of it being a product of evolution, but it's this. Instead, it's a product of cultural evolution, shaping this weird, incredibly designed invention to wrap around our evolved minds and fit it perfectly.
Right. Wow. I'm off to buy Harnessed.
It was great talking to you, Russell.
And I encourage everybody else to do. Mark, you've been a really inspirational and fascinating guest, and I've learned so much, and I think it's been superb. So thank you so much for your time with us today, and really appreciate all you've said and done for us.
Thank you.
Take care.
Bye-bye.
Thanks for listening today. I hope we really got some value from that. I certainly enjoyed it myself. Remember, there's only other podcasts and with tools and techniques, different speakers and different resources available in this series of Resilience Unravelled, so please feel free to subscribe. Why not also drop across to Facebook and join